Hi everyone, I am Tamara Raschka, a PhD student in the AI and Data Science group of Professor Holger Fröhlich at the Fraunhofer SKY in Germany, and today I'm going to present our poster on AI-based clustering and characterization of Parkinson's disease trajectories. The main idea behind this work comes from the fact that Parkinson's disease causes a wide variety of symptoms, including motor and also non-motor symptoms. These symptoms, as well as the general progression rate of the disease, is highly variable across patients. And this variability can also then impede the design of disease-modifying trials. So we therefore aim for a stratification of PD patients into subgroups, which are more homogeneous progression subtypes. Such a classification can then help to provide a better disease understanding and in the end also higher success rates of clinical trials. The underlying method is here the deep learning method, a variational deep embedding with recurrence or shortly VADA. It gives the possibility to identify progression subtypes from longitudinal patients' disease trajectories by implementing a multivariate time series clustering. We used the VADA algorithm to cluster multivariate longitudinal progression data of Parkinson's disease patients from the PPMI study. And we used here a combination of 6 different clinical outcome scores, namely the 3 UPDR scores, Epworth Sleepiness Scale, Tremor Dominance, and also the Postural Instability and Gait Disturbance Parameter. From this analysis, we can identify 3 subtypes, a fast, moderate, and slow progressing one. The mean trajectories of the progression clusters can be seen here, where the red line corresponds to the fast progressing cluster and the green line to the slow progressing one. The summary statistics of patients per subtype at study baseline showed no significant differences of confounding factors like gender or the time since diagnosis. But we see a significant difference for the age across clusters, such that slow progressing patients tend to be younger, which matches the literature. We also wanted to see which features are linked to the differences in the progression, so we trained panelized linear models to find such associations. We always trained the 1 versus rest classifier per cluster, and from this analysis we show here the top 20 positively associated variables and also the top 20 positively associated biological pathways. The most relevant findings here for the fast cluster, that it has a heavy effect shows a heavy effect of hallucinations, as well as it has a high association of pathways concerning the Golgi ER transport. The major player here is the VEGFA gene, which is also already discussed as a target in the literature. For the slow progressing cluster, the main associations are with the PARC16 locus and also the GBA gene. The last one is also an already well-known Parkinson's disease gene. Although we saw no differences in the symptomatic therapy response at the start of the study, we observed considerable differences in their response to the treatment over time, which you can see here in this figure. And that means that different drugs may benefit different disease subtypes better or worse, which leads in the end then to, or can in the end lead to personalized treatments, interventions, and prevention. Overall, these results contribute to a better disease understanding and give the possibility to stratify patients into subgroups based on their potential progression and the opportunity to design better clinical trials and novel drug targets. Future work will focus on transferring and validating the longitudinal progression clusters to multiple other Parkinson's disease studies. Thanks for listening to my poster presentation.